0.9 repeating. Here's something that's often confusing. 0.9 repeating, by which I mean 0.9999999, just going on like that forever. That is equal to 1. Not just close to 1, not a little bit less than 1. This is exactly equal to 1. There's a few different ways to think about this. For example, you might already believe that 0.3 repeating, right, 0.3333, and so on, is equal to a third. Now, if I multiply all of this by 3, what happens? Well, if I multiply this by 3, I get 0.9 repeating, right? If I multiply 0.33333 by 3, I get 0.99999. But if I multiply a third by 3, I get 1. We can also formulate this in terms of a series. So I can instead think about it this way. 0.9 repeating is the sum, n goes from 1 to infinity, of 9 times 10 to the negative n. Well, why is that? Well, what's the first term here? What happens when I plug in 1? That's 9 times 10 to the negative first power. When I plug in n equals 2, that's 9 times 10 to the negative second power. When I plug in n equals 3, that's 9 times 10 to the negative third power, and so on. Well, what are these? Right? 9 times 10 to the negative first power is 9/10. 9 times 10 to the negative second power is 9/100. 9 times 10 to the negative third power is 9/1000, and it keeps on going. Well, what's 9/10? That's 0.9. What's 9/100? That's 0.09. What's 9/1000? That's 0.009, and it keeps on going. And when I add these up, well, what I end up with is just a 0.9 from here. This 9 gives me a 9 here. This 9 gives me a 9 here. The next term gives me the next 9, and so on. I end up with 0.9 repeating. We can evaluate that series. So this series is 9 times the sum n equals 1 to infinity of 10 to the minus n. And I can make that look even more like a geometric series. It's 9 times the sum, n goes from 1 to infinity, of 1/10 to the nth power. Now, how do I evaluate that? Well, I've got a formula for summing an infinite series like that. It's a geometric series whose common ratio is between 0 and 1. So that converges, and its sum is 9 times the first term is 1/10 divided by 1 minus 1/10. What is that? That's 9 times a tenth over 9/10. Well, what's a tenth over 9/10? I could multiply the top and the bottom by 10, and I'd get this is 9 times a ninth, and 9 times a ninth is 1. And this discussion brings up an important point. Any time that we're writing down decimals, I mean, if I just make up some number like 0.57896, and imagine it keeps on going. Anytime I'm writing down real numbers like that, I'm secretly writing down a series, right? What do I even mean by ... I really mean a series. I mean that this is the sum, n goes from 1 to infinity, of d sub n times 10 to the minus n, where these d sub n's are the digits, right? d sub 1 is 5, d sub 2 is 7, d sub 3 is 8, and so on. Right? So anytime I'm writing down a decimal expansion, I'm secretly writing down an infinite series just by adding up all the decimals. To make it a little bit clearer, let me just write down the first few terms, right? N equals 1 and d sub 1 is 5 means that this is 0.5. And to 0.5, I'm adding the n equals 2 term, which is d sub 2 is 7 times 10 to the minus 2, which is 0.07. And then I add the n equals 3 term, which is 0.008. And then I'll add the n equals 4 term, which is 0.0009, and so on. So all of these decimal representations of real numbers are secretly just a series. So when thinking about real numbers, or at least their decimal representations, we're led naturally to think about series.